All right, we are going to finish talking about photons and photon interactions, and we're going to jump right into nuclear physics, which sounds a lot more impressive than it is. So we're going to do a little of both. And let's kind of review and add a little more for photon interactions. We've really hit the big things, right? Photons can do a few different things. Photons can cause the photoelectric effect, where a photon strikes an electron and knocks it out of orbit. That's the first thing that we looked at. Which is called the photoelectric effect. The second one, unfortunately, doesn't really have a name, but electrons can be knocked to a higher excited state by a photon, which we also looked at. It can go to various energy levels, and then it would de-excite and give off photons to drop back down, which is also what we looked at. The other thing that could happen is a photon strikes an electron or a nucleus, or really any atomic or subatomic particle, right, and just give away some of its energy. This actually has a name, not that it's vitally important, but this is called Compton scattering. There we go. It's actually called the Compton effect, which is basically say the photon can strike something and give away some of its energy, but it won't give away all its energy, right? So it could strike something. We could even argue that this happens with electrons in number 2. Sometimes it has more energy than the electron can handle, so it strikes the electron, moves it up to a higher level, but then another photon is emitted, or we could say that photon changed, right? We could kind of look at it either way. Either a second photon is instantly shot out of the electron, or the photon that struck the electron keeps going. It just has less energy, right? So kind of either way we could look at it, and that's called the Compton effect. And I could actually do it in lots of cases, right? If it hits anything, it could certainly hit that and give away some of its energy, and then a second photon or the photon changes and keeps on going, right, with less energy, which isn't that big of a deal, but it can happen. And then we understand that if the photon loses energy, it still doesn't slow down. Photons are going the speed of light. So what will it do? It'll have a decrease in frequency, or it'll have an increase in wavelength if it loses energy. And then the last thing that can happen, which is kind of a unique one, is a photon can create matter and turn into a positron and electron. So a photon that essentially is a bundle of energy can actually turn into things with mass. An electron, we know what it is, right? It is the particle that orbits the nucleus of an atom. We can look up its mass, which we've had to do in various problems before. We can look up its charge, which we know is the elementary charge, negative 1.602 times 10 to the negative 19. A positron is not the same as a proton. A positron is a positively charged particle that has the same mass as an electron. So it's very similar to an electron, except it has a positive charge, but it has the same mass. So this is what we call pair production. And we're going to have a very specific equation that governs this situation of pair production. But really, once we're going into nuclear physics, we're going into a different area that kind of violates, or we have to look at situations that go against some of the rules that we were talking about already. So we'll get into that, but these are the different things that a photon can do. Now, regardless of whether it's a photon or not, if a photon strikes the nucleus of an atom, now that nucleus of the atom has extra energy associated with it, and it doesn't have to get that through bombarding it with photons. Other things can hit it, and we'll see that, right? There's other interactions that could occur that will give the nucleus of an atom more energy, and therefore making it unstable, because the protons and neutrons have more energy than they're used to, and they're moving around faster. When that happens, the nucleus tends to de-excite, just like the electrons were de-excited back down to ground state. But again, they do it in very specific ways. There's certain ways that a nucleus of an atom that has too much energy, or is unstable because it has too much energy, there's certain ways that it tends to de-excite. Sometimes it gives away energy and mass, sometimes it just gives away energy. So let's kind of go through these, and we'll look at, we should understand what happens in these types of decay. We should understand how to write the chemical equation for these, and then later we're going to look at the equation that governs how much energy is released. But we've all seen the equation before, even though we've never used it. So the first thing that can happen is alpha decay, and alpha decay is when a helium nucleus, not a whole helium atom, right? Alpha decay is when whatever we have gets rid of a helium nucleus, right? So we could say it's a helium nucleus. We'd also say it's an alpha particle. So some people like to call it a helium nucleus. Some people like to say, well, it's not really a helium nucleus, it is an alpha particle, right? So either one, first of all, the symbol for alpha decay is this, and we could see that an alpha particle has an atomic number of 2, which means it has 2 protons, right? And has an atomic mass of 4, which means it has 2 protons and 2 neutrons. So basically, if we have an atom and that atom is extra excited, and therefore if the nucleus is excited, therefore unstable, one of the things it could possibly go through is it can go through alpha decay, where it ejects 2 protons and 2 neutrons, which means the atom that's left is now a different element, right? It is a different element by 2 protons and 2 neutrons. So for example, I'm going to look it up and we're going to find something that goes through alpha decay. There's quite a few things like radon does. And there's others. I should have had this open to the appendix, but bear with me one second. All right, something that goes through, there we go. I'm in the right spot now. No, I'm not. All right, I think I will just make up one. Here we go. Sorry about that. So let's say we have uranium-232. So we have uranium. We're going to maybe write this a little different way than we're used to, but let's say we have uranium. So there is my element. It has an atomic number of 92. So that's how many protons it has. And if you're not used to writing it this way, then this is the way we're going to write it, right? So then we have our atomic number, 92. And then we are going to have our atomic mass, which can certainly vary. But this time we're going to say it's 232. Now, 232, uranium-232 isn't stable. The nucleus is excited, and therefore it can't stay in this format. So it is going to de-excite, and when it de-excites, well, one of the things that it's going to get rid of is an alpha particle. Again, we can call it He if we want, or we can call it an alpha particle. But when we're done, what are we going to have left? Well, it used to have 92 protons. It lost 2, so now it's going to have 90 protons. And what has an atomic number of 90 is thorium. So it does change, right? Which is the big part of nuclear physics, right? It's the one situation where an element turns into another element. And then it lost 4 in its atomic mass because 2 protons, 2 neutrons. So this is going to be 228. So this is one form of decay, or we could even say it's one form of radiation. The nucleus ejects this, and now what I'm left with is this. So that's alpha decay. We could say a few more things about alpha decay, right? Alpha decay, if you have things that are going through this radioactive decay and are going through alpha decay, we understand that if we breathe it, it's extremely damaging because we have a fast-moving, massive particle, right? This has a charge of +2, so it's charged, and it has a mass of 4. And so for things that are breaking off from the nucleus, this is a very big, highly charged piece. So it's actually very damaging. If you breathe in material that's going through alpha decay, then that could be extremely damaging to your lungs if you get some way to internalize it. But on the flip side, because it is so big and so charged, it tends to be shielded easy, right? Paper, a sheet of paper tends to block it. Your skin tends to block it, right? So it's not really dangerous if it's on you. It is dangerous if it gets inside you. Just to kind of point out what type of radiation we're talking about, and is this exceptionally damaging, right? It has it's easy to shield, but it is massive and highly charged. So one thing that an atom can go through is alpha decay. Another thing that an atom can go through is excited and go through beta decay. Now, alpha decay, it tends to give off an alpha particle, which is the same as a helium nucleus. Beta decay really kind of opened people's eyes because of the things that are ejected. And understand, these things come out of the nucleus of the atom. So one thing, there's 2 types of beta. There's beta minus decay, and with beta minus decay, an electron is ejected. But again, the electron is ejected from the nucleus of an atom, which opens the door to a lot of misunderstandings and things that we're working on today, because once people realize what happens with beta decay, then the next question is, well, we didn't think electrons were in the nucleus of an atom. And that stuff, that's still getting worked out, but we do know it's an electron that leaves through beta minus decay, right? The other things that's possible is not a proton, but again, a positron, which is just like an electron, same mass as an electron, but the opposite charge. So it also could be beta plus decay, where a positron leaves, right? So we have two forms of beta decay. So let's say we have, now this one's using carbon, and I don't know if I mind using carbon. So let's say we have carbon. I'm going to write it better so we could see it. So it's 6C14, carbon 14, and let's say that carbon 14 goes through beta minus decay. Well, which means, first of all, we have this electron. An electron essentially has no mass, right? If we looked at it, if a proton, let's hope this makes sense, if a proton had, let's say, a mass of 1, then an electron would have a mass of 0.0005, right? It's a small amount of mass. So essentially it's not there. So if we go through beta minus decay, it's an electron that leaves. An electron has no mass, but it does have a charge of -1, right? And that charge of -1 leaves the nucleus. So what am I going to be left with? Well, my mass didn't change. It's still going to be 14. But now it's going to have 7 protons, which tells us something's happening, right? We believe that the neutron, a neutron, is getting rid of some negative charge and therefore turning into a proton, right? That's what we believe is happening. But now it turns into something else. So it's no longer carbon. It is now nitrogen 14, right? Which is the same thing that's written in the pictures. I'm just writing it out. So this is beta minus decay. We see what we have. We lose a -1, we lose a negative charge and no mass, so now we're left with something that has an extra proton and the same mass. Written here is another example of beta plus decay, which we're getting rid of a positron. So what does this one say? Let's see, what's something that goes through beta positive decay? So carbon 11 is a good example of that. Carbon 11 is something that could. So and if we said that had a nucleus that was excited, and in order to de-excite it went through beta plus decay, well then now it is something with a positive charge. It's getting rid of a positron if it's beta plus decay. Still no mass, because a positron is like an electron in the sense it has no mass. We're going to put P for positron, and then what does it turn into? Well, it's still going to have a mass of 11. But now it's going to, well, a positive charge left, which means it has one less positive charge, so now it's going to be 5. And if carbon 11 goes through beta plus decay, it is now going to turn into boron 11. So these are two examples of beta decay. We have beta minus decay, we have beta plus decay. And again, we want to see the chemical reaction. This is what we call nuclear chemistry, which again, very simple, right? We're not even adding different things. We are changing one element or one atom into another element, right? That's what's happening by removing things from the nucleus. So there's one more kind of big one, but it doesn't have the same, well, I should say there's a couple more. But the next one is gamma decay. Gamma decay is what we're already talking about, right? If we go back to this idea of Compton effect, where a photon strikes a nucleus and then a smaller photon is created, or it turns into a smaller energy level photon, right? This is Compton effect. And then that new one doesn't go slower, it just has a lower frequency because it has less energy. Well, gamma decay is kind of like that, right? Gamma decay is the nucleus is excited, and to de-excite itself, it gets rid of a gamma ray. Well, what's a gamma ray? A gamma ray is a photon. It's just another word for a photon. I don't know why they don't call it photon decay. They don't. But when it's excited, it gets rid of a photon. Well, a photon has no charge. It's a packet of energy, right? So it has no charge. It has no mass. So we have this parent that goes through gamma decay. What does it turn into? Well, it doesn't turn anything. It's the exact same thing, just the nucleus is less excited, right? So nothing really changes except it simply de-excites itself. So something that can go through this is beryllium-7. So it has 4 protons and it has 3 neutrons, and when it has an excited nucleus, it goes through gamma decay, so it gets rid of a photon, and that will de-excite the nucleus. But in the end, what do we have? Well, we still have beryllium-7. So these are the big forms of decays, if you will. Alpha decay, helium nucleus, or an alpha particle. Beta decay, beta negative gets rid of an electron. Beta positive gets rid of a positron. Or gamma decay gets rid of a photon, right? These are the basic forms of decay. But there's one more big thing that can happen. If we excite the nucleus of an atom and it's already very big and very unstable and we excite it, it can also go through fission. When it goes through fission, it breaks up into all these other pieces. And this is how it tends to happen. It's actually a pretty good example. Sometimes it just spontaneously goes through fission, right? There's certain materials that do that. But most of the time in a nuclear reactor or in a nuclear bomb or something like that, then we have to get the process started. We have this target nucleus like this, and it's on the tipping point. It's got an unstable nucleus. Nothing's really happening, but if we mess with it a little bit, we're going to get it to break apart. And why is that? Well, let's say that we have this nucleus, and I'm not going to draw it as big of a nucleus, but it actually works the bigger it gets. And we have a couple protons. So there's a proton, and there's a proton. Well, a couple things we know. We know from chemistry, and we're going to see it a lot in electricity coming up, right? Things with the same charges repel each other. So two protons near each other, right? There's an electrical force that's trying to push them apart, right? That's part of bonding. We know with bonds, then unlike charges attract and like charges repel. So we have these protons that are like charges. So the electrical forces are trying to push them apart. But they're not coming apart. It's a nucleus. They're staying together. So there must be another force, which is what we call the nuclear force, and that force is holding them together, a lot like gravity. It's simply holding them together because they're so close to each other and they got mass. Now, the thing is, though, the nuclear force only works over very small distances, where the electrical force works over relatively big distances. So if we have a small atom with just a couple protons and a couple neutrons, the nuclear force, they're all close to each other already, and the nuclear force is just going to hold them together. So it doesn't really matter this force of repulsion between the protons because the nuclear force is greater. But if we keep adding more and more things to this, then what happens is, well, the electrical forces don't really change. But now, like if this was a proton and this was a proton, then the electrical force between these two is basically the same, but the nuclear force is weakened because these two are farther apart. So the more things we add, the weaker the nuclear force gets, but the electrical force stays the same. So we start to get these atoms that are relatively unstable. And if you've looked at the periodic table, which I know you have, right, then most of the elements at the end don't last very long, right, because the nuclear forces aren't strong enough to hold it together. So they last for microseconds and milliseconds, and then they disappear, right? Because they simply can't stay like that because the forces trying to hold them together are not strong enough compared to the forces trying to break it apart, right? So they form for a moment and they break apart, right? So one of the ways they break apart is through fission. This picture kind of shows what normally happens if we want fission to occur is we make an element that's very unstable and it's ready to break apart, and then we smack another neutron into it. That causes the nuclear force to go down a little more, which causes the electric force to win, which basically makes it explode. It explodes into pieces, fission products, and then it also can break into and release a couple more neutrons. And breaking up into these couple more neutrons is important because if this needed one neutron to hit it to break apart, when it breaks apart, it gives 3 more neutrons. Well, then these can smash into the next 3 atoms, and they'll break apart through fission. And then they'll each make 3 more neutrons, which will turn into 9 reactions, and then those will each release 9, so there'll be 27 reactions. We can go on and on and on and on, right? But this process is going to cause fission, and it's going to make more byproducts that can cause fission more often. But fission is essentially breaking apart an atom into pieces. So if I had something that went through fission, let's say it's uranium-235, which is the fuel we tend to use in nuclear reactors. Uranium-235. There we go. And it tends to not fission on its own, so we need to give a little help. So we have a neutron, which has a charge of 0, has a mass of 1, and that's a neutron. And that goes through fission. Well, we could say, you know what, let's say that this turns into, well, one thing it turns into is xenon, so 54. It doesn't always do this. It's going to break up into different pieces, right? It's an explosion. So there's certain things that it tends to do. Oops, that's 54, sorry. There's certain things that it tends to do, but certainly it doesn't break the same way when it explodes. So let's get rid of this. this. So let's say xenon 132 is made. Then what else will we get? Let's see. And if it breaks into two pieces, well then the other piece, 54 is xenon. I said I didn't write it. So let's say one of the products when it breaks apart is xenon. Well then we know that there still is another 38 protons. And if we assume that the other piece, and it could make more pieces, but we're just giving an example. Then the second thing that it breaks up into is strontium. And then it usually breaks apart and releases some neutrons, and 3 is about right. The picture really does kind of show it, so it breaks up, and then it also gives off 3 neutron pieces that will now move on and interact with other particles. There we go. So I have 235, 236, so I have 236 atomic particles, right, for the atomic mass. And so far I have 132, 33, 34, 35. So this has got to be strontium 100, which is one possibility when it goes through this nuclear reaction and goes through fission, right? And then if we look, though, we would see a couple things. One, we would see strontium 100 is not a normal isotope, so this would rapidly de-excite, and this would go through its own form of decay, alpha decay, beta decay, would break apart, right? Might even fission itself, right? And this isn't super stable either, so that would go through another form of decay, right? That tends to go through, actually, xenon 132 tends to be stable, but the strontium is definitely not stable. So when we go through fission, it breaks up into these fission products. Again, it balances the same way. The positive, the protons all have to add up, and the protons and neutrons, the atomic mass, has to add up. We tend to see this, and if we're creating energy through fission, because when this explodes, all of these things have kinetic energy, right? So if we created energy by making something fission, a lot of the byproducts, a lot of the products are also radioactive or unstable themselves, right? It's one of the biggest hazards of a nuclear power plant. Once you use all the fuel that goes through fission, now you get all these pieces that you made, and they're still going through alpha, beta, and gamma decay, right? Because what we made was basically unstable. And then we have to let that decay and that decay until eventually it turns into something that doesn't go through decay anymore. All right, so those are the forms of decay when a nucleus gets excited. Alpha decay, beta decay, positive and negative, gamma decay, or it can go through fission. The other thing that could happen, though we don't see it happening here, it happens on the sun, and it's actually very hard for us to create, is nuclear fusion. And nuclear fusion is when certain atoms combine together to make something bigger, and then energy is created in that case too. Right? So this would be a proton and a neutron, and a proton and two neutrons. If they're moving at high energies, they can combine and fuse together, which makes sense. Fusion definitely occurs with smaller things. So if they could overcome the electrical force, and they tend to have to be moving fast, and they get close enough to each other, then the nuclear forces will start to pull them together, right? But that's hard to do because we have to get them close enough for the nuclear forces to win. Whereas when they're far apart, the forces of electrical repulsion tend to be winning. So you kind of have to get them moving really fast so they're practically smashing into each other. And then once they get close enough, nuclear forces can pull them together, and that would be fusion. Then it will turn into something bigger than it was, tends to release a small piece, and it gives off energy. So there are different examples of nuclear physics or nuclear reactions that can occur, and all of these are balancing equations, right? And the only other thing, which we'll do in some examples, that we have to know is, okay, well, how much energy is released? If we get something and it goes through, let's say, alpha decay, well, how much energy do we expect this alpha particle to leave with? Because if it gets shot out, it's now going to have kinetic energy, right? It broke free and now it's moving. So how do we determine that? Well, we determine that with Einstein's very famous equation, E equals mc squared. We'll do examples of these in the next lecture, but basically what we're saying is that the same thing that we saw with this pair production, we have a photon with no mass turns into two particles that both have mass, right? And this is the first time that people were starting to be able to figure this out. But basically we're saying that energy can turn into mass, right? Or vice versa, mass can turn into energy. So there is a transfer from one to the other. And how are they related? Well, they're related through the speed of light squared. So this violated a lot of things, right? This violates the conservation of energy, which is the foundation of physics, right? Energy cannot be created nor destroyed, only altered in form. Well, look at that, it can, right? We could turn mass into energy, or we could take energy, which is a photon, and we could turn it into mass. So these things can happen. We can gain energy and lose energy. But if we do that, then we're either gaining and losing mass, right? And then the other thing it violates is the conservation of mass, which is the complete foundation of chemistry, right? Mass can't be created or destroyed. It all has to be somewhere, right? And it was this idea about mass that broke us away from people thinking alchemy was what happened at this level and changed to the field of chemistry, right? Conservation of mass was really what governs these things. So this idea equals mc squared, but we could make energy from mass and we could make mass from energy, right, violated the foundations of two main sciences. Now, that in itself is not really a tragedy, to be honest with you, because in the end, it doesn't really violate both sciences, or it does, but it does in very certain places. So I'm going to kind of give a rough, I hate when this happens, hold on. I'm going to give a rough sketch here after I get rid of these and see what I'm talking about. So we could say, you know what, chemistry and physics don't work. Here we got Newton's law, which shows that, you know, this whole idea of conservation of energy doesn't work, but we spend a whole long amount of time looking at conservation, and we will too with electricity. It's based on conservation of energy. And then again, fields in chemistry, the same thing. So we can say, oh, well, chemistry doesn't work either. Look, we found it's wrong, but not really, right? If we looked at something, and I'm going to have the numbers wrong, I'm just going to kind of, if we looked at a graph, and this graph was mass versus speed, then we would see when we're dealing with masses that are extremely small, we're dealing with masses of electrons and protons and quarks and all these some subatomic particles. We're dealing with these tiny masses. Then now we're in this not Newton. We're dealing with Einstein's laws. We're dealing with relativity and the special theory of relativity. And we're dealing with a lot of different things. We're dealing with nuclear physics. So when we're dealing with masses that are very small, then we're in a kind of different type of physics and chemistry. Also, when we're dealing with things that are very big, or not very big, very fast, right? Once we start approaching the speed of light, and we get over half the speed of light, or like 2/3 the speed of light, and I don't know the number really, but once we get close to the speed of light, well, now the laws that we've learned in class, they don't really hold true yet anymore either, because now we're dealing with relativity. I shouldn't have started writing it, but now I got to finish it. Relativity. So now we're dealing with the laws of relativity, which creates mass, which warps time, which all kinds of crazy things happen. So when we get to deal with things that are extremely small, the Newtonian physics that we learn doesn't 100% apply. There are restrictions, and there are things that just simply don't work. When we get things going extremely fast, again, the things we've learned up to this point don't really apply, because time's distorted, mass is distorted, size is distorted. So many things get distorted when we go really fast. If we make things really big, well, then again, we have this issue. But right in here, when we're dealing with normally sized things that are going at normal speeds, well, then everything we learned that we like to call Newtonian mechanics, or things based on Newton, conservation of energy, Newton's laws with forces, Newtonian, all in here, well, then the laws of physics and chemistry, well, they work just fine. All right, we will do some examples with E equals mc squared in the next lecture, but we should understand the types of things that can happen to the nucleus of an atom, and we should be able to write a balanced equation on those.